This lecture will cover the CFA Level I reading on common probability distributions. A quick recap first of random variables. A discrete random variable is one where we can list all the possible outcomes, and for each possible outcome there is a measurable positive probability. A good example is stock price. So if the stock price is currently 45.01, stock prices move in ticks. So in Pakistan, for example, one tick is equal to 1 paisa. So the distinct values that the stock price can take is 45.02, 45.00, and so on. Also, if you roll a die, the possible outcomes are discrete random variables because the possible values are simply 1, 2, 3, 4, 5, and 6. A continuous random variable is where the number of points between the lower and upper bounds are essentially infinite. Example, rate of return. So again, if your stock is at 45.01 and you are trying to model the possible returns over the next year, the stock price could be anything over the next year, and the return, if the stock price is say 47.52, so the return will not be an exact number, so it will be a decimal that will go on and on. So trying to say that the return will be say 2% or 10% would not be 100% accurate. We'll see this in more detail shortly. Probability distribution. This basically is the probabilities of all possible outcomes for a random variable. When we say probability function, this specifies probability that a random variable takes on a specific value, and this generally applies to discrete random variables. If we are talking about a continuous random variable, then we refer to the probability density function. So let's look at an example now of a discrete uniform distribution. The simplest example would be the rolling of a die. So the way we can look at this discrete uniform distribution, on the x-axis we'll have the possible outcomes. So the possible outcomes when you roll a die are 1, 2, 3, 4, 5, and 6. And the probability of getting each one of these outcomes is the same. So that's why this is called uniform. Discrete because there are 6 discrete values, uniform because the probability of each value is 1/6. Some basic terminology now. The way we can express this is probability that x is equal to 1. X is the random variable. So probability that x is equal to 1 is equal to 1/6. Similarly, probability that x is equal to 2 will be 2/6, and so on. We can also say things like probability 1 less than equal to x less than equal to 3. So this would be 1, 2, and 3. So this would be 3/6. You should also understand the concept of cumulative distribution function. So cumulative distribution function, this is generally depicted by the letter f. So when we say f2, this means what is the total probability up to and including 2. So how much, starting from negative infinity, how much probability do we accumulate till 2 and including 2? So this answer would be 2/6. So the total amount of probability starting from negative infinity up to 2 is 1/6 and 2/6. So similarly, f3 will be 3/6. f6 will be 1, because up till 6 we have accumulated the entire probability, and if 7, 8, 9, etc. will also be 1. So if we come all the way beyond 6, basically we have then accumulated the entire probability. Now let's talk about a binomial distribution. To understand a binomial distribution, we must first understand the concept of a Bernoulli trial, because this is the building block of the binomial distribution. So the simplest example of a Bernoulli trial is a coin toss. The possible outcomes would be heads or tails. Let's say that we define, when we toss a coin, we define heads as our success, and we denote heads as 1 and tails as 0. The property of a Bernoulli random variable is that there are only 2 possible outcomes, and the probability of success is always the same no matter how many times you perform this trial. So no matter how many times you flip a coin, as long as it's a fair coin, the probability of success will always be the same, which is 0.5. This is denoted as P1, or Py is equal to 1, where y is the random variable. So when the probability that the random variable takes on a value of 1 is denoted as P, and in the coin toss example, P would be 0.5. The probability of a failure then, denoted by 0, would simply be 1 minus P, which for a fair coin would also be 0.5. Now let's talk about the binomial random variable x. This is simply the number of successes in a given number of Bernoulli trials. So let's say we perform n Bernoulli trials. Continuing with the example of the coin toss, let's say that we toss a coin 10 times. So that means that n is 10. The binomial random variable will be the number of successes. Now, what are the possible values of the binomial random variable x for this example where we are tossing a coin 10 times? It is possible that we get 0 heads, in which case the binomial random variable would be 0. It is possible that we just get heads once, twice, and so on, and the highest possible value would be 10. So the binomial random variable x can take on these possible values. Now let's just do this experiment. So take a coin and let's start tossing it. Let's say the first time we toss we get heads, second time heads again, then we get a string of some tails, then heads, tails, heads, heads, and so on. So how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, and finally let's say we get tails. So we performed this experiment, we flipped the coin 10 times, so basically 10 Bernoullis made up this one binomial experiment. And what's the binomial random variable? So it turned out that in this case x is equal to 1, 2, 3, 4, 5. So we had 5 successes because we had defined heads as a success. So in this particular binomial experiment, we came up with the random variable equal to 5. If we run the experiment again, then x might be something else. It might be 4. Run it again, it might be 7. So x is a random variable because before we conduct this binomial experiment, we don't know what the value of x will be. But what we do know is that it will be between 0 and n. Now let's understand the probability function. The probability distribution of a binomial random variable for the probability of x successes in n trials is calculated using the following formula. So let's continue with the coin toss example. What's the probability of getting 5 successes if we are doing 10 coin tosses? And the answer to that is given by this formula. So the probability of getting x successes in n trials is ncx times p to the power of x. P, remember, is the probability of success. X is the number of successes times 1 minus p to the power of n minus x. Now what's P5? So P5 would be 10C5 times P was the probability of success. In our example, it's 0.5 to the power of x, which is also 5, times 0.5 to the power of 5 again. So that is the probability. You can calculate this, and that will be your probability of getting 5 successes. What's the probability of getting all 10 successes? So that would be 10C10 into 0.5 to the power of 10 actually, because we have 10 successes, times 1 minus p, which is 0.5 to the power of 10 minus 10, which is 0. So this will cancel out because that's simply 1. 10C10, how many ways can you select 10 out of 10? And the answer to that also is 1. So we'll simply be left with 0.5 to the power of 10. Now what's the logic of this formula? The way you can think about this is as follows. We are saying what's the probability of 5 successes over here. So one way this can happen is if we have heads, 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 heads and heads 5 times, and then tails, 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 tails 1 time. So this, what's the probability of this? The probability is 0.5 to the power of 5 successive heads, and then this would be 0.5, which is the probability of getting a tail, to the power of 5, because we have 5 successive tails. So that gives us this part of the expression. Now the order of success doesn't matter. It doesn't matter that the successes have to be all in a row, or we don't have to have a situation where the successes come first. You can have any combination of heads, tails, as long as we have 5 heads. So that is why we have this combination term. In how many ways can we get 5 heads out of 10 tosses? So that explains the 10C5. If you got the logic, that's great. If you didn't get the logic, not such a big deal. What you must do is memorize this formula and understand the application. So probability of getting x successes is equal to ncx, where n is the number of Bernoulli trials within our binomial experiment, times p, probability of success, to the power of number of successes, into 1 minus p, probability of success. So this becomes the probability of failure, to the power of n minus x, which is the number of failures. A simple example now. Assume the probability of a stock going up on a given trading day is 0.6. What is the probability that this stock will be up on 3 of the next 5 trading days? So whenever you get a question dealing with the binomial distribution, you need to settle the values of n, x and p. So what is n? Since we are talking about the next 5 trading days, n is equal to 5. The success is defined as a stock going up, and that probability is 0.6. So p is equal to 0.6, and what's the probability that stock will be up on 3 of the next 5 days? So that means x is equal to 3. Now going back to the formula, so probability x is equal to 3 is equal to ncx into p to the power of x into 1 minus p to the power of n minus x. Let's plug in. N is 5, so we have 5c3 into probability of success here is 0.6 to the power of 3 times 1 minus p, which is 0.4 to the power of 5 minus 3, so that's 2. You can do the calculations and the answer that you should get is 0.3456. Now let's talk about the mean and variance of a binomial random variable. For a Bernoulli, B1P simply means that let's take the coin flip example. So we are flipping the coin once. P stands for the probability of success. So for a coin flip, P would be 0.5. Now the mean value or the expected value is simply 0.5 and the variance is 0.5 into 0.5. What's more interesting is the mean and variance for a binomial. So BNP means that you are flipping the coin n times, so you are doing n Bernoullis, and P is the probability of success every time you do a Bernoulli. What's the mean value? The mean value is n times P. This is easy to understand with our coin flip example where we have B10, comma 0.5. So 10 coin flips, probability of success is 0.5 each time. So what is the mean value? The mean value would be 10 into 0.5, which is equal to 5. This is saying that if you do the binomial experiment thousands of times, so thousands of times you do a set of 10 coin flips, then on average you can expect to have 5 heads or 5 successes, which is somewhat intuitive. Now, what does variance mean? Again, let's say that you are performing this binomial experiment where one binomial experiment is the combination of 10 Bernoullis. So if you do this many times, let's say that the first time you do this you get x equals to 5. Next time you do it you have x equals to 4, then x equal to 7, then x equal to 3, and so on and so on. So clearly there is a variance here. So we've already said that the mean value is 5, and then there'll be some variance around this mean. Sometimes we'll have x more than 5, at times we'll have x less than 5. The lowest possible value will be x equal to 0. The maximum possible value will be x equal to 10 in this experiment. So what is the variance? We don't need to know the derivation, but simply need to know this formula, that the variance is n times p times 1 minus p. In this example, n is 10, so the variance is 10 into probability, which is 0.5, times 1 minus p, which is also 0.5. So this is simply equal to 2.5. So the variance is 2.5. What if we have b n is equal to 5, p is equal to 0.5, then the mean is 5 into 0.5, which is 2.5, and the variance is n into p, which is 0.5 into 0.5, which is 1.25. If you do a binomial experiment with 5, n equal to 5, and the probability of success is 0.1, then the mean becomes 5 into 0.1, which is 0.5, and the variance would be 5 into p, which is 0.1 into 1 minus p, which is 0.9, and that will give us 0.45. Example, a bond portfolio with 25 European issues from distinct issuers has an estimated annual default rate of 10%. What is the expected number of defaults in the portfolio, assuming a binomial model for defaults? So what was the expected number? Expected number is n times p. What is n? We have 25 issues times p. probability here, the success is defined as a default, so into 0.1, 10%, so that is equal to 2.5. What's the variance? Variance is n into p into 1 minus p, which is 25 into p, which is 0.1 into 0.9, and you can do the maths there. A binomial model can be applied to stock price movement. The way we make this work is we define two possible outcomes and the probability that each outcome will occur. So let's take a simple example. Say a stock price currently starts at S, and the two possible outcomes are that the stock price goes up or the stock price goes down. And let's say that the probability of going up is 0.6, the probability of going down is 0.4, and this is the up probability, this is the down probability. And if the stock price goes up, let's say that it goes up by a factor of u, so we can say that the probability that the stock price will go up is 0.6, and if it goes up, then the new price is u times s. And if the stock goes down, the probability is 0.4, and let's say that the down factor is d, so 0.4 going down, the price then is d times s. Now we can just continue with this. In the second stage, again, probability of going up is 0.6, and the new price will be u times s, and this will be u times d times s, and this probability is 0.4. Here we'll have going up probability 0.6, going down probability is d ds, and so on. So this experiment, we can just keep going with this, but this is simply an example of a binomial model applied to stock price movement. So take an example. Let's say a stock is priced at $10 and has a 60% probability of moving up, 40% probability of moving down. So 0.6, 0.4. If it moves up, it increases by a factor of 1.06. So if it moves up, then the price would be 1.06 times 10. And if it moves down, it decreases by a factor of 1 over 1.06. So if it goes down, then the price becomes 10 divided by 1.06. And what is the expected stock price after two successive periods? So this is what happens after one period. What happens after the second period? The stock if one possibility is the stock goes up and then the stock goes up again. So this probability is 0.6. If it goes up again, the new price will be 1.06 squared into 10, and this probability is 0.4, and the value here 1.06 into 10 divided by 1.06, so that's essentially back to 10. From this point we can go up. The probability is 0.6, and here again this would be 10 divided by 1.06 multiplied by 1.06, so back up to 10. And if we go down, the probability is 0.4, and the new value is 10 divided by 1.06 squared. So if you do the probabilities, the probability of being at the stop point is 0.6 into 0.6. So the probability is 0.36. The probability of here coming to this middle node is 0.6 into 0.4, which is 0.24, plus 0.24 from here. So this probability is 0.48. And finally, the probability of being at the bottom node is 0.4 into 0.4, which is 0.16. The expected value here then is 0.36 times this value plus 0.48 times 10 plus 0.16 times 10 over 1.06 squared. And if you do all these calculations, the answer that you should get is 10.27.